about going into dark energy, dark matter? I mean, there's a difference in that area. Can you explain both of them, so to speak?
Sure. So dark matter was discovered first, and to be clear, we discovered evidence for dark matter in the 20th century. First evidence for it was from studying the motions of galaxies within clusters of galaxies. Galaxies like our Milky Way are rarely isolated in space. Most of them exist in groups. Our galaxy and the Andromeda Galaxy, sometimes called M31, are the two biggest galaxies in what we call the local group of about 24 galaxies, most of which are much smaller than ours. But there are some systems of hundreds or even thousands of galaxies, and those are called clusters of galaxies. And an astronomer named Fritz Zwicky, who was at Caltech in Pasadena, he studied the motions of the galaxies in clusters and saw that they were moving much faster than he expected. Now, why do I say faster than he expected? Because if you add up the mass of all the stars and all the gas in these galaxies, there's a certain amount of gravity from that mass. And the more gravity you have, the harder it's pulling on things that are orbiting around it, and so the faster they go. So, and it's just like in our own solar system, the closer you are to the sun, the faster you orbit. So Mercury goes around in 88 days. It takes the Earth, which is farther out, 365 days. So the motions in these galaxy clusters appeared to be much faster than you could account for with the gravity of the visible galaxies. And in fact, the motions were so fast that those galaxies should have been flying away, but they weren't. They were part of the cluster. So what Zwicky inferred, he didn't observe it, but he inferred that there must be more gravity in these clusters than is represented by the visible stars and gas. So he called it dark matter. Now, for many years, people assumed that the dark matter was probably just things that we don't see, like planets, which only shine by reflected light. You can't see planets in distant galaxies. Or maybe they were burned out stars, or maybe they were black holes or something like that. But when you look at where black holes come from, and you look at the masses of planets compared to stars, and you look at all these things, you realize that there's no way that the amount of mass in galaxies or burned out stars could possibly add up to all the matter that would be required to produce the gravity to hold these galaxy clusters together. So we began to have this notion that there's some other kind of matter that doesn't shine and that we don't see any evidence for except by its pull of gravity. So this is we call it non-baryonic dark matter, because baryons are the particles that make up ordinary matter, and ordinary matter gives off light, it absorbs light, it interacts with gravity, it feels friction, things like that. Dark matter is thought to behave differently. It pulls with gravity, but it doesn't feel friction, it doesn't shine, it doesn't absorb light. So the next advance was Vera Rubin in the 1970s. She was measuring the rotations of spiral galaxies, galaxies like our own Milky Way. And she made a discovery that was similar to that of Fritz Zwicky, who was looking at galaxy clusters. She discovered that the outer parts of galaxies were moving so fast that they should be flying away from the galaxies. And the only way that they could be that those galaxies could be held together was if they too had much more mass than you could account for by the stars and the gas and the dust and everything that you see in the galaxies. So those were the two major steps in the discovery. What we say is the discovery of dark matter. What it really is the discovery of motions that imply that there's more gravity there, more mass there than we can see. And so by the 70s, 80s, we were pretty sure that dark matter was real. Well, in the late 90s, let me back up. So now, everything in the universe, every mass in the universe pulls on every other mass. And if everything is pulling on everything else, then as the universe expands, which is something that we've known has been happening since Edwin Hubble in the 1920s, also Georges Lemaitre, a Belgian priest who was also a cosmologist, he and Hubble both were working on this problem. Hubble published first, and so, or at least published in English first, so he gets most of the credit. But he discovered that the farther out you look, the faster galaxies are moving. It's as if they're the result of some kind of explosion. Everything's moving away from everything else. And the farther away things are, the faster they're moving. So it looks like the universe is exploding or expanding. And we figured, well, if everything in the universe attracts everything else, that expansion should be slowing down. So the farther and farther out you go, you should see that the rate of expansion should be slowing because everything is tugging on everything else. So several teams of astronomers went out to measure that deceleration, and instead they discovered that actually the farther out you go, the faster and faster the expansion is going. It looks like something is pushing the galaxies apart even faster than they would ordinarily be going. And so we call that force dark energy, not because we're in the dark about what it is. That's why it's called dark energy, and it's also analogous to dark matter. We're in the dark about what dark matter is too. So we now think that there's more dark matter in the universe than there is ordinary matter, and that there's more dark, and that, Einstein said E equals mc squared, which means if you have energy, it can be converted to mass. If you have mass, it can be converted to energy. So we often think of mass and energy as interchangeable. So if you add up all the mass and energy in the universe, it looks like the stuff that you and I are made of adds up to less than 5%. And then about a quarter of the universe appears to be dark matter, and 70% of the universe appears to be dark energy. So astronomers find themselves in this very curious position where we have what we think is a really good understanding of the origin and evolution of the universe and the galaxies and stars and planets that we see around us, but we don't know what 95% of the universe is made of. So there's still some serious problems.
There's some work to be done.
Yeah, definitely some work to be done. A work in progress. Yeah.
So is dark matter and dark energy, can we say they're related?
They're related in the sense that they both account for, one of them, dark matter is attractive. It's the pull of gravity. Dark energy you could almost think of as anti-gravity because it's repulsive. It's pushing things apart. So they're like yin and yang, or the opposite ends of a spectrum. They're related because they're both the major constituents of the universe, and we don't yet know what they are. But the effects that they have on objects in the universe are kind of opposite. One would tend to pull things together and slow them down, and the other one would tend to push them apart and speed them up. They're both very important frontiers in astronomy. And another area where they might be related, and this is kind of interesting and strange, is when we're talking about the universe and galaxies, we're talking about the very large, right? The largest scales we know. But we now think that dark matter is probably some kind of particle, some kind of, something like a proton or an electron or a neutron or a subatomic particle. But it's a kind that we haven't discovered yet. We're looking, there are numerous experiments. When astronomers try to imagine, if you were going to create a particle that had gravity but didn't feel friction and didn't give off light and didn't give off heat, what would the characteristics of that particle have to be? And so particle physicists who work on the very, very small, have come up with some ideas about what those particles might be like. And then they predict how those particles might occasionally interact with ordinary matter. And so physicists and astronomers have collaborated to build instruments to try to detect this stuff, but so far we haven't detected anything. Dark energy is thought to be a force, um, you know, some kind of field that pushes things apart. The other forces that we know, gravity, poles. Einstein tells us that gravity is a curvature of space-time. You can think of curved space. Think of a bowling ball sitting on a rubber sheet, and how the bowling ball, makes a depression in the sheet. And if you roll a marble toward the bowling ball, it's going to fall into that depression. It behaves very much like something is pulling it in. Well, gravity is a force. We have forces within the atom, forces that act on very, very small scales, like only within an atom, but not outside an atom. And then you have the electromagnetic force, which does operate, at scales larger than atoms, but is not generally thought to be particularly important for the evolution of the universe, in the sense that most of the universe, gravity, over large scales, gravity seems to be the dominant force. And stars and planets and things, they don't carry a net electrical charge anyway. But so dark energy presumably also is some kind of force that's created at the subatomic, nuclear, atomic level, but we don't know what it is. We know of gravity, two nuclear forces, the electromagnetic force, and there's this other thing, and we don't know what it is yet. So it's a mystery, but we're working on it, and we've built a number of telescopes to try to measure the expansion history of the universe so precisely that we can figure out how dark energy behaves, how it affects the motions of galaxies across cosmic time. And if we can characterize how it behaves, we may have a better idea of how it's generated and what its origin is. But it's a big problem, and it's probably not going to be solved right away.
Should people today be more concerned about what's going on in research and the direction of your profession?
Well, I don't know what you mean by concerned. I think we're discovering more all the time. We're revealing splendid cosmic vistas through the imaging that our telescopes are doing. We're learning about all kinds of interesting things that are happening in the universe. Seeing black holes up close for the first time, watching stars explode. But we, if you're interested in trying to learn more and more about the universe, you should be heartened by the fact that astronomers are discovering things that they don't understand, and it gives them new avenues to pursue. I think we have a pretty good understanding of things, but there's always more to learn.